Welcome back. Let's talk a little bit about calorimetry today. It's actually a lot of review. If you recall, we actually talked about calorimetry a couple times across this class. We actually even did a lab about calorimetry. Remember with the coffee cup and put the little metal block in there and everything? Yeah, we've done calorimetry before, right? So let's kind of refresh our memory. Remember that calorimetry is about energy transferring either to or from an object into water inside a container. That container that we use for calorimetry is called a calorimeter. A calorimeter is well insulated. It allows us to measure the amount of heat transferred or absorbed in whatever way inside the container so we can then use it for calculations. So there's a description of this in your book way back in page 64 through 69, but just recall that the way that we're going to be handling calorimetry equations or calorimetry problems is by mostly relying on the formula of Q of the metal equals Q of the water. And remember that Q can be defined as Q equals mc delta T, where m is the mass, C is the specific heat, and delta T is the change in the temperature. So the amount of energy transferred between the metal is the amount of energy either absorbed or released by the water. It just depends on if it's an endothermic or an exothermic process. A lot of the times for us in calorimetry, especially in our experience in the past, we've done exothermic things where the metal is releasing heat into the water. So let's look at a couple examples maybe to refresh your memory. Suppose that we have 100 grams of water at 22.4 degrees Celsius and it's placed in a calorimeter. A 75.24 gram sample of aluminum is removed from boiling water at a temperature of 99.3 degrees Celsius and is quickly placed in a calorimeter. The substance reaches a final temperature of 32.9 degrees. Determine the specific heat. This is exactly like the experiment that we did together in our class. So again, there's a lot of values here, but if we keep ourselves organized, then it's not that hard at all. Remember that what we were talking about, like we said before, we said the Q of the metal equals the Q of the water, right? So you could break these equations apart if you want. You could have you could have mc delta T. And if you want, you could label them like this if you wanted to, or you don't have to. You know, like one or the other. It just kind of depends on how thorough you want to be. I'm going to choose to not label anything right now, just so I can keep myself nice and organized. So we know that one side is the metal and one side is the water. Now you might be thinking to yourself, well, you know, this isn't going to work, right? Because our delta T is going to be negative on one side and not negative on the other. Well, understand that specific heat can't be a negative number. So for now, we're just going to kind of assume that we're taking the absolute value of our delta T's in order to get ourselves a positive number in the end. So just keep that in mind. If you're calculating and you notice that you get a negative delta T, or excuse me, a negative specific heat, just flip the temperatures to make it not negative because specific heat can't be negative. But we are looking for the specific heat of the metal. So this is the thing that we are trying to calculate. So what I'm going to do is I'm actually just going to kind of manipulate this equation a little bit to solve for what I want. And now, you know, I've actually kind of changed my mind. I am going to label things. So this is the specific heat of the aluminum. And over here, I have the mass of the water, specific heat of the water, the change in temperature of the water, and that's divided by the mass of the aluminum and the change in temperature of the aluminum. So again, I have all these things available to me. They're all in the problem. The mass of the water, let's see if we can find it. Let's see, boom, right there, right at the beginning. So that's the mass of the water. That's 100 grams. The specific heat of water is something that you should just have kind of rattling around in your brain. It's 4.18 joules grams degrees Celsius. And then the temperature or the change in temperature of the water, like I said, let's just keep it at an absolute value to make this as easy as we can possibly do. The water started at 22.4 degrees Celsius and it reached a final temperature of 32.9 degrees Celsius. So you could, of course, do this outside, like maybe, or you could just put it right in, honestly, like this minus that. I'm just going to kind of do it outside and then plug it in. So that's 10.5 degrees Celsius. On the bottom, I have the mass of the aluminum, which is given to me right here, 75.24 grams. So that's 75.24 grams. And then I have the change in temperature of the aluminum. And this is what I was saying before. If you don't take the absolute value, this is going to be a negative number because this is a release in energy. Because we go from 99.3 degrees Celsius and we go down to 32.9 degrees. So I'm just going to take the absolute value of that, which should be just 66.4 degrees Celsius. Go ahead and plug this into your calculator and punch it up and see what you get. Come on back once you've calculated it. So you should get 8.79 joules per gram Celsius. So that's it. That's how you calculate specific heat. It's really just a lot of plugging in things and solving for what you need in the calorimeter. Why don't you try one? A 25-gram piece of metal at 75 degrees Celsius placed in the calorimeter, 25 grams, 20 degrees Celsius. The temperature stopped changing at 24 degrees Celsius. What is the specific heat of the metal? So same process. Go back and look at the previous question to see if you can run through it. I might not even show the work on this one. I might just trust you to do it. So come on back when you finish so you can check your answer. Okay, so hopefully this is what you got. I got 0.86 joules per grams degrees Celsius. Now, again, I'm not going to show the work for this because I just kind of trust you to be able to knock it out. If you're having any problems, make sure you bring it to me and we'll work through this together. But let's keep going. I know this is the end technically in your notes, but I'd like you to take some time and add just one extra little problem for me in the back of your notes. This is a really important problem. I don't know why this says NaOH like this, but this should be NaOH like that. Okay, so it's really important because it is relevant to the lab that we're going to do. So if you need to take a second and pause and write this into the back of the notes, that'd be great. Please don't ignore this. It's really important for you to be able to work something out like this. I'll show you how to do it. It's really easy. So 1.1 gram of NaOH is added to 100 milliliters of water at 22 degrees Celsius. Once all of the solid had dissolved, the temperature of the water was found to be 25.2 degrees Celsius. So the first thing, is the dissolving of NaOH endothermic or exothermic? Let's think about this. That means that in the process, the NaOH would be releasing energy while it's dissolving. So let's look at the temperature. We went from 22 degrees Celsius to 25.2 degrees Celsius, which means our temperature increased in the water. Where did that energy come from? It must have come from the NaOH. So that means this process must be exothermic. That's all it takes. It's as easy as that. If the temperature of the water went up, exothermic. If the temperature of the water went down, endothermic. And if you were like holding the flask or something while you're dissolving NaOH, you would actually notice that the flask gets pretty warm. It's a pretty endothermic process. I mean, 22 to 25 degrees, it's a pretty big jump. So yeah, exothermic, that's easy. Now let's calculate the heat of solution for NaOH. So in other words, like how much heat is involved in the dissolving of NaOH. Now understand that this equation is going to be kilojoules per mole. We're looking for the amount of heat released in this process. So the first thing we want to do is figure out kilojoules. We're going to figure out kilojoules by using our Q equals mc delta T. So Q equals mc delta T. And we're going to do it for the whole system. But things are going to be a little bit different. One thing in particular is that the m is not just going to be the mass of the water, but it's also going to be the mass of the NaOH. So that means we're going to have this 1.1 grams and the 100 milliliters of water. Remember that 100 milliliters is the same thing as 100 grams. So that plus 101 gives us our grams of 101 grams. I don't know why my writing got a little sloppy there at the end there. 101 grams. So we are going to use that 101 grams, and that's what we're going to plug into the M. The specific heat, we're just going to use the specific heat of water. I'm sure the solution has a little bit different of a specific heat, but we're just going to use the specific heat of water because it's not that much that we're dissolving. And then the change in temperature. So that should be 3.2 degrees Celsius. Go ahead and work this through and see what you get. Some uncomfortable sig figs here because you have to round a little bit, but it's okay. We'll deal with it. So it's 1400 joules, but remember we're looking for kilojoules. So that means we need to turn this to 1.4 kilojoules. Now, we're almost there. We now have to figure out moles. So we're going to take our kilojoules value and we're going to divide it by the moles of NaOH. Luckily, we were given grams of NaOH at the beginning, and we can, of course, go from grams to moles. That's the easiest thing in the world. I'm actually just going to kind of do it under here. So that's 1.01 grams, and we're going to divide that by the molar mass, which is actually 40 grams per mole for NaOH. And you should find that after you do this, this gives you what's called the heat of solution, which is 51 kilojoules per mole. Now, before we're done, we have to ask ourselves, are we reporting this number correctly? Is this an exothermic or an endothermic process? Well, we said up here that it was exothermic. So that means we can't just put 51 kilojoules per mole. We have to put negative 51 kilojoules per mole because, again, it's exothermic. So Just keep that in mind. And that's all you have to do. So again, you're going to run through a very similar calculation in your lab, but I wanted to show you one first before you kind of experience it there. It's not very difficult. You just have to kind of keep in mind the mass. That's kind of the tricky part. And then the rest of it's pretty straightforward. And that's it. We're going to talk about Hess's law in the next video, so I'll see you over there.